All right, let's dive right in. Today, we are talking all about site characterization. And really, you can just think of it as learning how to read the story that a piece of land is trying to tell you. Seriously, every single field, every slope, every patch of soil has its own history, its own potential, and it's all written right there, if you just know how to look.
So what if you could do just that? What if you could actually read the land like a book? Well, that's pretty much what we're going to do today. We are going to learn how to decode the language of the earth right under our feet. By the end of this, you'll be a regular landscape detective.
So here's our game plan. First, we're going to decode the land by looking at its ancestry. Then we'll get into a soil's biography, which is literally written in its layers. After that, we'll talk about water and drainage, the flow of life, really. We'll get a bird's-eye view by mapping your ground. And finally, we'll uncover topography's hidden and super important influence.
Okay, first up, decoding the land. You know, if you really want to understand any soil, you can't just look at the surface. You have to go way back to the very beginning, back to its ancestry, or what scientists call its parent material. Now, this is so important. The parent material is the raw stuff, right? It's the geological starting point from which a soil is born. It could be weathered bedrock, maybe some ancient river sediment, or even volcanic ash. Whatever it is, this is what sets the stage. It basically dictates the soil's initial texture, what minerals it's going to have, its entire potential. You can think of it as the soil's DNA.
So what happens next? Well, once that parent material starts to weather and change, we're talking over thousands of years here, it starts to develop these distinct layers. And this is where we get the soil's biography, its life story, told in chapters we call horizons.
Just imagine for a second that you dig a big pit in the ground. You're not going to see just a uniform block of dirt, right? No way. You'd see this incredible cross-section, a soil profile, with all these different colors and textures stacked on top of each other. And each of those layers tells a totally unique part of the story, a story of rainfall, of life, and of a whole lot of time.
Right at the very top, we've got the O horizon. Think of this as the living surface, you know? The layer of fresh and decomposing leaves, twigs, all that organic stuff. It's like the soil's protective skin. And it's the bridge to the world above it.
And right below that, you'll find the A horizon, which you probably know as topsoil. This is where all the action happens. That rich, dark color is your first big clue. It's telling you that this layer is packed with decomposed organic matter, which we call humus. This is the main hub of biological activity, where you'll find all the roots, the worms, the microbes, everything that makes soil thrive.
If we keep digging, we hit the B horizon, or the subsoil. I like to think of this as the zone of accumulation. See, as water trickles down from the top, it carries these tiny particles of clay and minerals with it, and it drops them off right here. If you see reddish or yellowish colors in this layer, that's often a dead giveaway for iron oxides, which tells a long story about that soil's relationship with water and air.
And finally, we get down to the sea horizon. And this brings us full circle because this is the parent material we started with. It's the least weathered layer of them all, the foundation on which the A and B horizons were built. It gives us a direct peek into that soil's origin story.
So let's do a quick recap of the story. You've got the O horizon on top for organic matter, then the A horizon or topsoil, where life is buzzing, below that the B horizon, the subsoil, which is that zone of accumulation, and finally the C horizon, our original parent material. That's the basic structure you'll find in most soils out there.
Okay, so now let's talk about one of the most powerful forces that shapes all these horizons, water. I mean, how water moves through a soil, what we call its drainage, is just absolutely critical for everything, from growing crops to building a house.
So you've got two ends of the spectrum here. On one hand, you have well-drained soils, often sandy ones, where water just zips right through. Now, that's great for getting air to the roots, but it also means they don't hold on to water or nutrients for very long. On the other hand, you have poorly drained, often clayey soils. They can hold a ton of water, but they can easily become waterlogged, basically drowning the roots and starving them of air. The soil's texture really does dictate its behavior.
So, how can you spot a drainage problem when you're out in the field? Well, you look for clues. Are you seeing plants that just love water, like cattails? If you dig a hole, do you find these weird spots or splotches of different colors? That's called mottling, and it's a classic sign that the water table is moving up and down. And of course, the most obvious clue of all, does water just sit there in puddles after it rains?
The good news is we can manage this stuff. For simple issues, you might just need some surface ditches to redirect the flow. But for those more stubborn problems, especially on valuable farmland, you can install a subsurface drainage system, which is basically a network of buried, perforated pipes. It's a more permanent solution for getting that water table under control. Okay, so we've looked down into the soil profile. Now let's zoom way out. If you want to understand a whole farm or even a whole region, you need that bird's eye view. And for that, we turn to the incredible tool that is the soil map.
Now, a soil map isn't just some random drawing. It is a super careful map of different soil types all across a landscape. Scientists use everything from aerial photos to the shape of the land, plus a ton of on-the-ground fieldwork to draw these boundaries. What you get is this beautiful mosaic of the soils hidden just beneath the surface.
So, how do they even make these things? Well, it's a really cool systematic process. It all starts with describing the soil at a whole bunch of different points, then classifying what they find. After that, they actually draw the map boundaries, and then they collect samples to analyze back in the lab. And finally, and this is probably the most important step, comes the interpretation. What does all this data mean for farming, or for building, or for conservation?
But here's the catch with maps. Scale matters. It matters a lot. A big, broad, regional map is fantastic for general planning, but if you're trying to make a decision about one specific field, like where exactly to plant a certain crop, you're going to need a much more detailed map. A map's scale really determines how much detail you have and what you can reliably use it for. All right, for our final section, let's talk about something we can see without even digging a hole: the actual shape of the land. Topography. You know, the slope, the direction it faces, its position in the landscape, it has this massive hidden influence on the soil.
I mean, think about it. It's pretty simple, right? Water runs downhill. So naturally, steeper slopes have a way higher risk of erosion, which washes away that precious A horizon. Gravity also pulls water and nutrients down through the soil itself. That's a process called leaching. And where do you think all that eroded soil and those leached nutrients end up? You guessed it, in the low-lying areas, which often become these amazing zones of accumulation with deeper, richer soils. And that, right there, is the big takeaway. By just learning to read the contours of the land, you can start to predict where you might run into problems with erosion or wet spots, and also where you might find those hidden opportunities, those pockets of deeper, more fertile soil. You can literally see the problems and the potential before you even stick a shovel in the ground.
We have covered a ton of ground here, from parent material all the way to soil horizons, drainage, mapping, and the influence of topography. You now have the basic vocabulary of the land's language. So the real question is, what are you going to do with it? How will you use it to read the story beneath your feet, to make better decisions, and to help write a more sustainable future for all of us?